Hello there, and welcome back to The Sleepy Scientist, your nightly escape into the quiet corners of the cosmos. I'm so glad you're here. Whether you're tucked into bed, resting on the couch, or staring up at the ceiling with a curious mind that refuses to clock out, you've found a gentle place to unwind. Tonight we'll be floating far beyond Earth into the coldest places the universe has to offer. And don't worry, you won't need mittens. Before we drift too far, I'd love to know where in the world you're listening from. What's the local time by you? Are you winding down after a long day, or easing gently into an afternoon nap? Drop a comment below and let me know. It's always amazing to see how many corners of this strange spinning planet we all come from. If this quiet journey into deep space helps you feel a little calmer, a little cozier, or just a bit more curious, I'd be incredibly grateful if you gave this video a like and considered subscribing to the channel. It helps keep these bedtime voyages going, and you might just find yourself nodding off in the rings of Saturn or the mists of a nebula before you know it. Now, I should warn you, I always try to strike a careful balance here. I hope the video isn't so interesting that it keeps you awake, but if it does, well, at least you'll wake up knowing more about quantum freezing and the temperature of empty space than most people you'll meet tomorrow. So, fluff your pillow, close your eyes if you'd like, and let's begin our slow drift toward the frozen edge of the universe. A place where heat is a memory, time moves gently, and atoms barely dare to shiver. And just before we embark, this video is for educational and relaxation purposes only. It is not medical advice, and I'm not a sleep doctor, just a sleepy scientist. Let's begin with something deceptively simple. What is cold? It feels like the kind of thing you just know without needing to define. Step outside on a January morning, or touch the metal seatbelt buckle after a night in the driveway, and your body will tell you exactly what cold is. But in science, we like to be precise. And in this case, cold isn't really a thing in itself. It's the absence of something else, namely heat. Heat comes from movement. Every object, no matter how solid or still it may seem, is made up of atoms and molecules that are always jiggling, vibrating, or bouncing around. The more they move, the more thermal energy they have, and when they move a lot, we call that hot. When they barely move at all, that's cold. If we could zoom in far enough to watch the molecules in your cup of tea or the air around your pillow, we'd see a chaotic dance of collisions and vibrations. These little particles don't ever sit entirely still, unless they reach a place called absolute zero, but that's a story for a colder chapter. For now, just imagine that cold is like a pause button, slowly being pressed on the microscopic jittering of everything around you. Now, how do we actually measure coldness? Or rather, how do we measure how little heat something has? Most of us are familiar with two scales, Celsius and Fahrenheit. In the Celsius system, water freezes at 0 degrees and boils at 100 degrees. That feels intuitive. Fahrenheit, mostly used in the United States, puts water's freezing point at 32 degrees and its boiling point at 212. Why those numbers? Blame a 17th century physicist named Daniel Fahrenheit, who had some rather unique ideas involving saltwater mixtures and body temperature. It's charming, if a bit chaotic. Then there's the Kelvin scale, the scientific heavyweight of temperature measurement. Named after Lord Kelvin, this scale starts at absolute zero, the theoretical point where all molecular motion ceases completely. 0 Kelvin is equal to minus 273.15 degrees Celsius, or minus 459.67 degrees Fahrenheit. It's not just cold, it's the lowest possible temperature in the universe. No jumping jacks or hot tea could help you there. Kelvin is particularly useful in physics because it removes the concept of negative temperatures. If temperature is just a measure of energy, it makes sense to have a scale that starts at 0 energy and only goes up. No fussy freezing points, just a clean scale of motion from stillness to chaos. But let's return from space for a moment and talk about how humans feel cold. The perception of cold isn't just about the raw number on a thermometer, it's about how fast your body is losing heat. Step into a cold room wearing a t-shirt, and you'll feel cold. not because the room is aggressively radiating coldness, but because your body is rapidly transferring its heat into the cooler air around you. This is why a humid 2-degree morning might feel chillier than a dry -5-degree evening. Moist air conducts heat away from your body more efficiently, making you feel colder. Wind does the same thing, which is why meteorologists invented the term wind chill. It's not a made-up number, it's a way to describe how quickly your body's losing heat, and how that affects your comfort. And that comfort, by the way, varies wildly from person to person. Some people wear shorts in the snow like it's a badge of honour, while others are reaching for thermal socks as soon as the leaves begin to fall. Our skin has temperature-sensitive nerve endings that alert us to changes, but they're not perfect instruments. They're tuned more for survival than accuracy. Your fingertips might scream cold, even when your core temperature is perfectly stable. Interestingly, cold can sometimes burn. If you've ever touched dry ice or leaned against a metal pole in sub-zero weather, you'll know the sting of freezing pain. At extremely low temperatures, the cold causes water in your skin cells to freeze, expand, and rupture. It's the same damage caused by heat, but from the opposite direction. This is why frostbite and burns can look eerily similar. We tend to think of cold as an inconvenience, something to be battled with scarves and space heaters. But it's also a tool, a force that humans have learned to harness. We use it to preserve food, store vaccines, and slow down chemical reactions. Cold is the reason your leftovers don't turn into science experiments overnight. It's also why sperm banks and biological samples can be stored for decades without degrading. Cold slows time for living tissue, in a way that's almost poetic. Of course, there are limits. You can't just toss an organ in a freezer and expect it to work later. Freezing biological tissues creates ice crystals that can destroy delicate structures. Scientists have developed advanced cryopreservation techniques using special chemicals to prevent this kind of damage, but that's diving into the more extreme ends of the temperature spectrum. For now, picture the chill on a winter's morning, or the crisp bite of air in a high-altitude breeze. That sensation you feel isn't cold coming in, it's heat racing out of you, like a crowd leaving a theatre all at once. Your body notices the absence and it calls it cold. And yes, while your feet in the middle of January may feel like they've reached the temperature of deep space, I promise you, they're not quite the Boomerang Nebula. But they try. Oh, how they try. In truth, cold isn't an enemy. It's a natural part of the universe's balance. Heat moves from hot to cold not out of cruelty, but because that's how energy wants to spread. From stars to soup to skin, it's all about movement, and cold is just the name we give to stillness. As we continue this journey, remember, cold is not just something you feel, it's a state of the universe, a quiet, slowed-down version of reality. And sometimes, all it takes to appreciate it is a little curiosity, and maybe a good pair of wool socks. Let's take a gentle stroll through temperature yen, not the kind you get from a quick glance at a weather app, but a full-scale journey from the hottest heat to the coldest cold the universe allows. Imagine standing at the edge of an erupting volcano. Molten lava, freshly released from Earth's mantle, bubbles and flows at around 1,200 degrees Celsius. That's hot enough to melt most metals and destroy just about anything organic in seconds. It's also the kind of heat that screams danger, not just because it's destructive, but because it's a vivid reminder of how much energy atoms can store when they're bouncing around wildly. Now move a little cooler, only a little mind you, to the surface of the sun. There, temperatures hover around 5,500 degrees Celsius, go deeper into its core and things heat up to a staggering 15 million degrees. At that point, hydrogen atoms smash together and fuse, releasing vast amounts of energy and light in a process we call nuclear fusion. This process powers our daylight and fuels our seasons, all thanks to unimaginably high temperatures that make lava look like lukewarm tea. But those are the dramatic extremes. Most of the universe, it turns out, prefers a chillier demeanour. As we begin to slide down the scale, we pass the warmth of a summer's day, say 30 degrees Celsius. then a room temperature cup of tea around 20, then our own bodies, comfortably resting at about 37 degrees. Everything still seems familiar here, within the comforting middle of the scale where life tends to thrive. Keep descending, and we find freezing water at 0 degrees Celsius, followed by sub-zero winter mornings and the biting air of the poles. At minus 70 degrees Celsius, things start to feel alien. That's colder than Antarctica on its worst days. Below that, at around minus 196 degrees, nitrogen turns from a gas to a liquid, a favourite for science demonstrations where flowers shatter like glass. Go even further down, and we enter the realm of space. The emptiness between stars and galaxies is not just dark, it's also incredibly cold. Temperatures there hover around 2.7 Kelvin or minus 270 degrees Celsius. That's the temperature of the cosmic microwave background, the faint afterglow of the Big Bang that still permeates the universe like a whisper from its earliest days. It is, for all practical purposes, the baseline temperature of outer space. Now let's talk about a number so extreme, it's almost absurd. Absolute zero. 0 Kelvin. Minus 273.15 degrees Celsius. That's the theoretical point at which all atomic motion would stop completely. No jiggling, no vibration, nothing. It represents a kind of perfect stillness, a temperature so low that it doesn't really exist anywhere naturally, at least not in its purest form. Absolute zero is like the finish line of the temperature race. Not just cold, it's the absence of heat in the most complete sense, and yet, ironically, nothing in the universe ever quite gets there. Why not? Well, it turns out nature is pretty stubborn. According to the third law of thermodynamics, as an object approaches absolute zero, the amount of energy you have to remove increases exponentially. Each fraction of a degree closer requires more effort than the last. It's like trying to scoop every single grain of sand off a beach using only a teaspoon. You get close, but there's always a little more to go. Physicists have thrown some clever tricks at the problem. In ultra-cold labs around the world, they've cooled atoms to within billionths of a degree above absolute zero. That's incredibly close. So close, in fact, that the atoms start behaving in totally bizarre ways, forming states of matter like Bose-Einstein condensates, where particles act as one unified entity instead of individuals. These experiments use techniques like laser cooling, where carefully tuned beams of light slow down atoms by pushing against their motion, and magnetic trapping, which holds those slowed atoms in place. It's a bit like building a molecular hammock and gently rocking atoms into a nap. But even with all this precision, absolute zero remains just out of reach. It's a boundary, not a destination. In the cosmic sense, this limit is reassuring. If anything could reach absolute zero, the implications would be strange. For one, entropy or disorder would drop to nothing, which violates a lot of what we understand about how time and energy work. A perfectly ordered system doesn't behave well with the universe's usual messiness. The cosmos, it seems, prefers a little noise in the system. One of the more delightful quirks of the Kelvin scale is how cleanly it handles this concept. Since Kelvin starts at zero and only goes up, it aligns beautifully with energy. No negative kelvins, no fuss about freezing points or boiling points shifting based on pressure. It's the scale that tells you exactly how much energy is hiding inside a substance. A gas at 300 Kelvin is simply more energetic than one at 100, and that's that. Back here on Earth, we still toggle between Celsius and Fahrenheit for everyday life. Celsius has that pleasant symmetry of freezing at 0 and boiling at 100, which makes it intuitive. Fahrenheit, though, clings on in some parts of the world with its quirky 0 at saltwater freezing and body temp around 100 logic. It's like the quirky cousin of the temperature family, confusing but kind of endearing once you get used to it. And yet, no matter which scale you use, the sheer range of temperatures in the universe is staggering. From the searing infernos of stars to the frozen silence of interstellar space, the thermometer of the cosmos spans more than 15 million degrees from top to bottom. and nestled somewhere in that scale is you, listening in a room likely hovering around 290 Kelvin, give or take. A narrow comfort band in the grand scheme of things. Cold in all its quiet majesty is not just a temperature. It's a glimpse into how energy behaves when it begins to fade. A reminder that even the absence of heat carries meaning. From the sun's fusion to the background hum of the Big Bang, it's all part of a spectrum. And as you rest in your own warm corner of the universe, it's oddly comforting to know that even the coldest voids follow the same rules, just on a different setting. Absolute zero may be impossible to reach, but the journey toward it has taught us more about atoms, time, and the nature of energy than perhaps any other scientific pursuit. It's a horizon we chase, not because we expect to arrive, but because what we find along the way is quietly extraordinary. If you were to drift quietly through the southern skies somewhere in the direction of the Centaurus constellation, you'd eventually find yourself 5,000 light-years from home. Out there, beyond the reach of our solar system's warmth, hidden among the stars lies an extraordinary little patch of cosmic oddity known as the Boomerang Nebula. Now, nebulae are often places of drama. Some are birthplaces for stars, swirling clouds of gas and dust where gravity pulls together the ingredients for future suns. Others are cemeteries of the cosmos, remnants of stars that have lived long, burned bright, and finally let go. The Boomerang Nebula falls into the latter category. It's a planetary nebula, which, despite the name, has absolutely nothing to do with planets. Instead, it's the result of a dying star gently, or sometimes not so gently, expelling its outer layers into space. What makes this particular nebula so special, so uniquely chill in fact, is its temperature. Measured at just 1 Kelvin, that's minus 272.15 degrees Celsius. That's colder than the background temperature of space itself. And yes, that's just as strange as it sounds. Space is already about as cold as things naturally get, sitting at a frigid 2.7 Kelvin thanks to the lingering microwave radiation left over from the Big Bang. So how on Earth, or rather how in the universe, can anything get colder than that? To understand this frozen miracle, we have to look at how the Boomerang Nebula formed. The central star, now in its twilight years, began puffing out its outer layers in a rapid and spectacular fashion. The gas is streaming away at over 500,000 kilometers per hour. That's not just fast, it's staggeringly fast, like watching an elderly tea kettle explode into a hurricane. This gas, moving outward at breakneck speeds, expands incredibly quickly into the near vacuum of space. And when gases expand without any source of external heat, they cool down, rapidly. It's the same basic principle behind how your air conditioner works, or why compressed air feels cold when sprayed from a can. As the gas spreads out, its energy is dispersed over a greater volume, and the temperature drops. But the Boomerang Nebula takes this to a cosmic extreme. The expansion is so fast and so unimpeded that the gas cools to 1 Kelvin, below even the 2.7 Kelvin of the cosmic microwave background. The reason it can do this is quite clever. The dense cloud of gas itself acts like a thermal shield, blocking out the faint warmth of the background radiation. Inside that cocoon, temperatures can fall lower than the surrounding universe. It's like a natural deep freezer floating in space, crafted by a dying star. The nebula wasn't discovered until the early 1980s, when astronomers using radio telescopes noticed something odd. Observations at sub-millimeter wavelengths revealed that this object was emitting far less radiation than expected. In other words, it was cold, really, truly, extraordinarily cold. Later measurements confirmed that this wasn't just unusually chilly for a star's remains. It was the coldest naturally occurring place we've ever found. The name, Boomerang Nebula, came from its early appearance through ground-based telescopes. At low resolution, it seemed to have a two-lobed structure, like a boomerang mid-flight. Later, with sharper images from the Hubble Space Telescope, it turned out to be more hourglass-shaped, with jets of cold gas blasting outward from the central star and forming symmetrical wings of mist. a cosmic butterfly, if you prefer a more poetic image, albeit one made of pure frost. What's even more fascinating is that this entire frigid display is temporary. As the gas continues to expand and thin out, the chill will eventually fade. Light from nearby stars or even the ambient microwave background will begin to seep in. The gas will warm ever so slightly, and the Boomerang Nebula will rise back to the common cosmic chill of 2.7 Kelvin. For now, though, it remains a fleeting oasis of utter cold. It's a beautiful paradox. A dying star creating something so quiet and cold that it defies expectation. Stars are supposed to burn, to radiate, to flood the cosmos with energy. Yet here we find one, not in a blaze of glory, but in an exhalation of frost. It reminds us that space is full of surprises, and that endings in the cosmos are often as elegant as beginnings. You might wonder what it would feel like to stand inside the Boomerang Nebula. Assuming you could somehow survive the complete lack of atmosphere, the intense radiation, and the disintegration of your molecules at an atomic level, it would be, well, silent, motionless. Not in the peaceful way we think of a quiet night, but in the eerie, suspended way that comes when heat and motion have nearly vanished. It would be the closest you could come to standing inside a whisper. There's something deeply poetic about the fact that the coldest place in nature isn't some black dead corner of the universe. It's a star's final breath, a farewell made not in fire but in frost. It doesn't rage or roar. It sighs, and that sigh freezes into a magnificent shroud of mist and silence. Astronomers continue to study the Boomerang Nebula, trying to unravel more of its secrets. Observing it helps scientists understand the physics of gas expansion, stellar evolution, and even how molecules behave in ultra-cold conditions. It's not just an oddity, it's a laboratory, a naturally occurring experiment unfolding in the vast stillness of space. In a universe that often shouts, the Boomerang Nebula whispers. It drifts quietly, shedding its layers, painting the sky with invisible ice. And for a brief time, in a place 5,000 light-years away, cold triumphs completely overheat. A rare, fleeting glimpse of the universe at its stillest. Long before galaxies spun themselves into graceful spirals and stars began to twinkle their steady light, the universe was a hot, dense, chaotic soup. Everything we now see, planets, gas clouds, humming microwave ovens, was once packed together in a blinding, seething fog of energy and particles. There was no darkness, no cool air, and certainly no silence. Just an expanding blaze of raw existence. But time, as it often does, changed things. Around 380,000 years after the Big Bang, a blink in cosmic terms, the universe had cooled enough for atoms to form. Electrons finally settled into orbits around protons, creating neutral hydrogen atoms. This relatively minor event had a major consequence. The universe became transparent. For the first time, light could travel freely without bouncing endlessly off free particles, like a cosmic pinball machine. And that light is still travelling. We call it the cosmic microwave background, or CMB for short. It's the oldest light in the universe, a faint afterglow from a time when everything was still young and unformed. It's not bright, it doesn't flicker or sparkle, and you can't see it with your eyes. But it's everywhere, all around you, all the time, quietly humming through the air. The temperature of the CMB is an extraordinarily chilly 2.725 Kelvin. Just a hair above absolute zero. That's about minus 270 degrees Celsius. In terms of energy, it's barely there. But because it fills all of space, it's significant. It represents the minimum natural temperature of the universe. You can't go outside and find a cosmic location any colder than that without some very specific and unusual conditions, like in the Boomerang Nebula. The background radiation sets a kind of universal floor for temperature, the base hum of warmth that the cosmos has not yet managed to shake. Now calling it microwave might make you think of kitchen appliances and reheated leftovers, but the term refers to the wavelength of the radiation. After over 13 billion years of cosmic expansion, this ancient light has stretched dramatically, moving from the fiery visible spectrum all the way down to the long low-energy microwaves. If the universe hadn't expanded, this relic light would still be blazing in ultraviolet or X-rays. Instead, it has cooled right along with space itself. In the early 1960s, two radio engineers named Arno Penzias and Robert Wilson were working at Bell Labs in New Jersey on satellite communication. They kept encountering a mysterious static, an unexplained noise in their equipment. No matter what direction they pointed the antenna, the noise persisted. They tried everything to eliminate the interference, even clearing out a pair of nesting pigeons and more delicately what the pigeons left behind. But the static remained. What they had accidentally discovered was the cosmic microwave background. It wasn't noise from Earth. It was the sound of the universe's infancy, stretched across the sky and reaching into their antenna. For their serendipitous find, they were awarded the Nobel Prize in Physics in 1978. Since then, scientists have been mapping the CMB with ever-increasing precision. The first major map came from the COBE satellite in the early 1990s. It revealed that the background wasn't completely uniform. There were tiny fluctuations or anisotropies in temperature, no larger than 1 part in 100,000. These subtle variations were crucial as they seeded the formation of galaxies, clusters, and everything else that eventually turned into, well, us. Later missions like WMAP and Planck gave us incredibly detailed portraits of the CMB. These maps show a sky filled with faint blotches of warmer and cooler regions, not by much, just slight ripples, like the texture on a fine sheet of silk. But within those ripples lies a record of the universe's earlier structure. By studying them, scientists can determine the age, shape, and even the destiny of the universe. It's like reading the baby photos of all of existence. The background radiation is so consistent, so omnipresent, that even old analog televisions used to pick up a tiny fraction of it as static. If you ever remember watching a fuzzy channel and seeing that grainy snow, a small percentage of that flicker was actually the universe's own broadcast, older than galaxies, quieter than shadows. Interestingly, because this radiation fills space so evenly, it acts as a kind of cosmic thermometer. If you find yourself floating in intergalactic space, far from any stars or galaxies, the coldest you'll get, without some exotic shielding, is that same 2.725 Kelvin. It's a limit imposed by the past. The light from 13 billion years ago still has a say in how cold the present can be. You can't block it easily either. The CMB isn't just coming from one direction, it's coming from all directions. It doesn't beam toward you like sunlight, it envelops you. It is the light of the universe, frozen in time, stretched and softened, but never quite extinguished. What's truly beautiful is that this light carries information about everything it has ever touched. Scientists can measure the polarization, spectrum and directionality of the CMB to uncover hints about inflation, the incredibly rapid expansion of the universe just moments after the Big Bang. They can even search for the faint fingerprints of gravitational waves, the tremors of space-time itself. And yet, for all its cosmic importance, the CMB is gentle. It hums without urgency, glows without flame, and surrounds us like a memory. It's the universe's way of saying, I've been here a while. There's comfort in that. No matter how vast or chaotic things become, there is this soft, steady light behind it all. A cosmic nightlight that has never turned off. It also serves as a reminder of how deeply connected everything is. You, listening right now, are literally bathed in the light of the early universe. The atoms in your body, the signals reaching your ears, the warmth in your blanket. All of it exists against a backdrop of ancient glow. It's not romanticized poetry, it's physics. The cosmic microwave background may not dazzle the eye or stir the senses like a galaxy or a nebula, but its stillness is profound. It is the canvas upon which the rest of the cosmos was painted. A gentle echo from the dawn of time, still whispering across the void, asking us to listen, not with our ears, but with instruments, equations, and curiosity. It's easy to overlook something so subtle, but sometimes it's the quietest things that carry the deepest stories. Out between the stars, far from the warmth of any sun or the glow of any galaxy's core, there lies a strange kind of stillness. Not a peaceful stillness like a sleeping cat, but the vast sprawling kind, an emptiness that stretches for light years at a time. This is interstellar space, cold, dark, and almost completely devoid of matter. And yet, in its quietest corners, some of the universe's most astonishing transformations are quietly unfolding. If you could float through this emptiness without a spaceship or a woolly jumper, and let's imagine for a moment that your atoms somehow cooperate, you'd find the temperature holding steady at around 3 Kelvin. That's just a whisper above absolute zero. The cosmic microwave background radiation we talked about earlier sets that baseline. It gently warms the universe like a faint memory of the Big Bang, ensuring that even the most desolate voids never quite reach true stillness. Now 3. Kelvin might sound bone-chilling, and it is, but what's more remarkable is just how little there is in these spaces to feel cold in the first place. Interstellar space isn't truly empty, but it's close. A single cubic centimetre might contain 1 or 2 atoms. For comparison, the air you're breathing right now contains something like 25 billion molecules in the same space. You'd have to scoop up a volume the size of Earth just to gather enough interstellar gas to make a decent campfire. Despite this sparseness, these vast regions aren't entirely without activity. In fact, some of the coldest areas, oddly enough, are also the cradles of stars. These are cold molecular clouds, immense, shadowy regions where temperatures can fall as low as 10 Kelvin, and where new suns are quietly gestating. These clouds are made mostly of molecular hydrogen, with traces of helium, carbon monoxide, ammonia, and other more complex molecules. Dust particles too, tiny grains of carbon, silicates, and ices, float through the gas, helping shield it from starlight and keeping it cold. Without these dusty particles, ultraviolet radiation from nearby stars would break apart the fragile molecules and ruin the quiet chemistry at work. Cold is a key ingredient here. It allows atoms to slow down enough to form stable bonds. In hotter regions, collisions happen so violently that molecules break apart before they get the chance to settle down. But in these frigid clouds, atoms move gently. They bump, they cling, and gradually they begin to build. Not just hydrogen pairs, but more complex molecules like formaldehyde, methanol, and even the precursors to amino acids, the building blocks of life brewing in the coldest dark. Ironically, in order for something as fiery as a star to form, you need a place this cold. The reason lies in pressure and gravity. Warm gas tends to expand and resist compression. Cold gas, on the other hand, is more cooperative. It contracts more easily under the pull of gravity. When a dense pocket of gas and dust inside a molecular cloud gathers enough mass, it begins to collapse inward, slowly heating up as it does. Over time, that collapse becomes a star, hot, bright, and full of energy. But its birth is only possible because of the cold that came before. Astronomers can't see these molecular clouds in visible light because they absorb and scatter it. Instead, we detect them using radio telescopes and infrared instruments. They often show up as dark blotches against a backdrop of stars like smudges on a cosmic window pane. Some of the most famous are in the Orion Molecular Cloud Complex, a region not too far from the familiar belt of Orion. It's one of the most active nearby nurseries of new stars, filled with dense cores waiting for gravity to tip the balance. And these clouds aren't small. Some stretch for hundreds of light years. The cold isn't a temporary weather front, it's a long-standing condition, lasting millions of years. During that time, chemistry proceeds at a glacial pace. Atoms slowly find their partners, dust collects ice mantles, photons from distant stars bounce off particles and scatter into oblivion. It's not dramatic. It's slow, quiet work. But it lays the groundwork for solar systems, comets, planets, and maybe, just maybe, life. One of the more delightful puzzles is how fragile molecules survive in such a hostile environment. After all, space is filled with high-energy radiation, shock waves from supernovae, and the occasional rogue cosmic ray. But the same dust that helps keep the clouds cold also acts like a shield. It absorbs damaging photons and gives molecules a bit of privacy to go about their business. The result is a surprisingly rich and diverse chemistry, happening in places where the sun never shines. In some of the colder, denser cores of these clouds, temperatures fall even lower. Here, even carbon monoxide can freeze out onto dust grains, forming icy coatings that become chemical playgrounds. Under just the right conditions, ultraviolet photons can strike these icy surfaces and drive reactions that produce increasingly complex compounds. In laboratory simulations, researchers have even produced amino acids from these cosmic ice mixtures. It's like space is quietly rehearsing the recipe for life on the backs of dust particles in the coldest corners of the galaxy. Between galaxies, in the truly intergalactic voids, things are colder still, but ironically also more empty. These regions have so little matter that not even molecular clouds can form. Here, the temperature stays pinned close to the background radiation limit of 2.7 Kelvin. There's not enough material to do much of anything except drift. No stars, no chemistry, just particles passing each other like strangers on a moonless highway. Yet, even this emptiness is part of the cosmic story. The coldness of space defines the contrast that makes stars burn brighter, galaxies swirl more dramatically, and planets feel more alive. Without the cold, there would be no edge to the warmth, no silence to make the music of the universe stand out. Cold is not just absence, it's the necessary background for structure and life. In the chill of interstellar space, the universe is patiently at work, crafting the ingredients of suns and the molecules of life with the slow, steady touch of time. So while these regions might seem bleak, they're far from lifeless. They're pregnant with potential, quietly assembling the future out of hydrogen, gravity, and silence. In a strange way, the coldest places in the universe are also its most hopeful. They are where everything begins. While the coldest places in the cosmos may float quietly through the vacuum of space, some of the most astonishingly frigid environments are created right here on Earth. Tucked away inside laboratories filled with blinking lights, humming coils, and minds determined to do the impossible. Getting close to absolute zero, 0 Kelvin or minus 273.15 degrees Celsius, is no simple task. You can't just buy a better freezer. At that level of cold, ordinary concepts start to fall apart. Atoms move so slowly that they begin to blur into the world of quantum mechanics, where they behave more like waves than particles. To achieve this surreal state, scientists have developed incredibly clever tools. Tools that cool things not by subtraction, but by control. One of the most elegant methods is called laser cooling. Now, lasers might seem like an odd choice for chilling things down. After all, when most people think of lasers, they think of cutting metal, playing with cats, or pretending to be a Jedi. But in the right context, a laser can slow atoms down so effectively that they come almost to a stop. The principle is fairly straightforward, even if the math is less so. Imagine you have an atom moving in one direction. If you shine a beam of light, specifically tuned to a frequency the atom likes to absorb, in the opposite direction the atom absorbs a photon, which gives it a little push backwards. Do this many times from many directions, and the atom slows down. The less it moves, the less kinetic energy it has, and less kinetic energy means less heat. Using this method, scientists can reduce temperatures of atomic gases to microkelvins, millionths of a degree above absolute zero. And if they combine laser cooling with another trick called magnetic trapping, they can go even further. Magnetic trapping works by using carefully arranged magnetic fields to hold ultra-cold atoms in place, like invisible tweezers. Once the atoms are gently slowed by laser cooling, they're shepherded into this trap where the temperature can be fine-tuned using evaporative cooling. Yes, evaporative cooling, just like sweat on your skin. By allowing the hottest atoms to escape and trapping the rest, the average temperature of the group drops even further. These methods, used in tandem, allow scientists to reach temperatures unimaginably cold, nanokelvins, or billionths of a degree above 0 Kelvin. It's not quite the bottom of the scale, but it's astonishingly close. And it's in this environment that something very weird happens. Enter the Bose-Einstein condensate. Predicted by Satyendranath Bose and Albert Einstein in the 1920s, this state of matter wasn't actually created until 1995. It's what happens when a bunch of atoms are cooled so close to absolute zero that they stop behaving like individuals and start acting as one. Picture this. You have a group of atoms, each with its own little identity, dancing around and doing its own thing. But as the temperature drops, their individual quantum states begin to overlap. Eventually they become indistinguishable, one collective wave of matter. Instead of many particles, you get one giant particle. It's like a marching band so perfectly in sync that every footstep, every breath, every note is unified. These condensates are fragile, beautiful, and deeply strange. They don't behave like solids, liquids, or gases. They're their own category, a window into the quantum realm where the rules of our everyday world break down. You can't see a Bose-Einstein condensate with your eyes, but under the right instruments, scientists can track its delicate behaviour. They've seen waves ripple through them like sound in water, watched them tunnel through barriers, and even spin in tiny quantum vortices. Creating a Bose-Einstein condensate isn't just a scientific trick, it's a triumph of precision. Laboratories around the world have built specialised setups to make this happen. One of the first was at the University of Colorado Boulder, where Eric Cornell and Carl Wieman shared the Nobel Prize in 2001 for their success in creating the very first condensate from rubidium atoms. Since then, places like the Massachusetts Institute of Technology, Stanford, and institutions in Europe and Asia have all pushed the boundary further. These labs are home to the coldest spots on Earth, miniature voids where temperature is so low, it's hard to even call it temperature in the traditional sense. Some of these experiments have reached temperatures less than 1/billionth of a Kelvin above absolute zero. Interestingly, even space agencies have joined the chill. NASA launched a cold atom laboratory aboard the International Space Station in 2018. Without the interference of gravity, the atoms can be trapped and cooled for longer periods, giving researchers more time to observe their behaviour. It's a freezer floating in orbit, dedicated entirely to exploring the physics of ultra-cold atoms. Back on the ground, cryogenic research doesn't just live in theoretical physics. Superconductors, materials that conduct electricity with zero resistance, require extreme cold to function. This is the same principle that powers MRI machines, particle accelerators, and quantum computers. In each case, lowering the temperature reveals behaviours that are otherwise hidden. Cold, it turns out, is a kind of magnifying glass for the laws of nature, and of course, we shouldn't forget the more down-to-earth uses of cryogenics. Liquid nitrogen, which boils at minus 196 degrees Celsius, is used in everything from flash-freezing food to preserving biological samples to making very dramatic-looking cocktails at science museums. It's cold enough to make rubber brittle and freeze a rose solid. Handy, but not quite nanokelvins. What makes this all the more amazing is that none of these temperatures happen naturally on Earth. The planet's coldest recorded natural temperature, measured in Antarctica, was around minus 93 degrees Celsius. That's enough to freeze your breath into icicles, but it's still more than 180 degrees warmer than what's needed for liquid nitrogen, and many thousands of times warmer than the Bose-Einstein condensate labs. In those labs, temperatures are measured not with traditional thermometers, but through incredibly sensitive instruments that detect atomic motion, spectral lines and quantum behaviour. When atoms barely move at all, traditional ideas of warmth and coldness become abstract. You're not dealing with the thermometer anymore. You're reading the stillness of the universe itself. In the end, the pursuit of ultra-cold temperatures is less about breaking records and more about revealing truth. When matter slows to a crawl, the strange and subtle rules of quantum mechanics step into the spotlight. The randomness fades and the pattern emerges. It's like dimming the lights on a stage to reveal the faintest, most intricate choreography. So while the stars may burn bright and the universe may swirl with energy, some of its deepest mysteries are revealed only in the quiet chill of the coldest labs on Earth. It's there, in the near-perfect stillness that matter whispers its secrets. Slowly, precisely, and colder than you could ever imagine. As the temperature drops and matter cools, something peculiar starts to happen. It's as though the universe, in its frostiest corners, begins to peel back its everyday mask and reveal its stranger, subtler self. At high temperatures, everything feels familiar. Atoms vibrate, molecules collide, and energy flows predictably. But approach absolute zero, and the stage belongs to quantum mechanics. The rules change. The usual script of physics starts to stutter, and a new, more mysterious performance begins. To understand how weird things can get, let's start with the basics. At room temperature, atoms are energetic little dancers, jiggling and bouncing and whizzing around with thermal enthusiasm. Even in a solid object, atoms don't sit perfectly still. They vibrate in place like restless toddlers. But as temperature drops, their movement slows. By the time you're down to a few kelvins, atomic motion has all but ceased. It's not just cold, it's quiet. And in that quiet, quantum behaviour steps out of the shadows. One of the most dramatic examples of this quantum weirdness is a phenomenon called superfluidity. This occurs in liquid helium when it's cooled below about 2.17 Kelvin. At that temperature, helium undergoes a phase transition, not just into a colder version of itself, but into a completely different kind of substance. Superfluid helium does not behave like any liquid you've ever encountered. It flows without friction, not less friction, no friction. If you set it swirling in a container, it will keep spinning forever. Not for a long time, forever. There's no internal resistance to slow it down. It's like a liquid with zero memory of motion. No viscosity, no drag. Even weirder, superfluid helium can climb the walls of its container. Quite literally. If you pour it into a beaker, it will slowly creep up the sides and spill over, defying gravity like it's been possessed by some mischievous spirit of physics. It's not climbing because of heat or pressure. It's climbing because the laws of quantum mechanics allow it to. The atoms in the superfluid are so perfectly coordinated that they act like a single wave, flowing as one continuous coherent entity. There are no individual sloshing parts, just a united quantum whole. Helium is the only element that remains liquid at atmospheric pressure down to absolute zero. It refuses to freeze unless you apply pressure, which is unusual behaviour in the world of matter. That makes it the perfect playground for exploring these surreal properties, and scientists have spent decades plumbing its depths, often discovering more questions than answers. Another chillingly strange behaviour near absolute zero is superconductivity. It shares a family resemblance to superfluidity, but applies to electrons instead of atoms. Normally, when electricity flows through a wire, the electrons bump into atoms and lose energy as heat. That's why your phone gets warm or your toaster glows. But in certain materials cooled to below a critical temperature, often just a few kelvins, electrons suddenly stop resisting. They form pairs known as Cooper pairs and begin to move through the material without scattering. No collisions, no resistance, just perfect lossless flow. Imagine a city with a rush hour crowd that suddenly starts walking in perfect synchrony. No traffic, no jostling, just a serene river of motion. That's what happens in a superconductor. the material carries electricity with perfect efficiency, and the effect is powerful enough to levitate magnets, trap magnetic fields, and transmit energy with zero waste. It's not just a cool party trick, it has real potential for revolutionizing how we build power grids, MRI machines, and even quantum computers. Superconductors are usually made from complex ceramic compounds and require elaborate cooling systems, often using liquid helium. But researchers are constantly hunting for materials that become superconductive at higher temperatures. There have been some promising results, like materials that exhibit superconductivity at -135 degrees Celsius, but we're still a long way from finding one that works in your garage on a Tuesday afternoon. Then there's the way time seems to behave differently at these temperatures, not in the sci-fi sense of travelling through wormholes or freezing clocks, but in the way quantum systems evolve over time. As energy levels drop, the fuzziness of quantum mechanics becomes more pronounced. Particles can tunnel through barriers they shouldn't be able to cross, occupy multiple states simultaneously, and interact in ways that seem to defy logic. In warmer conditions, this behaviour is usually washed out by thermal noise, random jostling that hides the delicate quantum choreography. But near absolute zero, the noise fades. Quantum coherence, the idea that particles can remain in a stable, linked state over time, becomes more visible. This is crucial for fields like quantum computing, where maintaining coherence is key to building reliable quantum bits, or qubits. In essence, extreme cold slows the universe down just enough to let us observe its subtler details. You might say that cold is the lens through which we glimpse the fine print of physics. The rules haven't changed, they're just easier to read when the atoms aren't shouting over each other. One especially poetic feature of near-zero physics is the emergence of order. As temperature drops, disorder, the random bouncing of particles, reduces. And at these ultra-cold limits, systems tend toward more structured, unified states. It's a counterintuitive twist. The colder things get, the more elegant and cooperative they become. Atoms synchronize, electrons pair up, fluids defy gravity. It's as though the universe is whispering its secrets, but only once the noise of heat has been turned all the way down. There's a quiet beauty in this, a kind of cosmic minimalism. At room temperature, matter is lively, messy, and complicated, but lower the temperature, and complexity gives way to unity. Atoms align, particles merge, and motion becomes a gentle dance instead of a chaotic scramble. It's the universe at its most refined and very, very cold. Of course, we're still only scratching the surface. There are undoubtedly more surprises waiting in the deep freeze of the quantum world. Every time physicists think they've mapped the landscape, they stumble across another oddity, a strange oscillation here, a new phase transition there. The physics of near-zero temperatures is one of those areas where the more you understand, the more mysterious it becomes. It reminds us that cold isn't just a nuisance or a backdrop, it's a powerful tool, a key to unlocking behaviours that defy everyday experience. From superfluid helium to levitating magnets and quantum waves that move as one, the chill near absolute zero reveals a version of the universe that's usually hidden. And in that stillness, in that almost perfect quiet, matter shows us what it's capable of when all distractions are stripped away. So, if you ever find yourself thinking of cold as empty or lifeless, remember this: the deepest magic often requires the quietest stage, and near absolute zero, the universe gives its most elegant performance. For all the incredible feats modern science has accomplished, splitting the atom, landing robots on distant planets, decoding the human genome, there's one stubborn boundary we just can't cross, a line we inch toward with ever-increasing precision, yet never quite touch. That boundary is absolute zero, 0 Kelvin, the ultimate stillness, the point where atomic motion stops, entropy reaches a minimum, and the universe shrugs its coldest shoulders. And despite our best efforts, we truly cannot get there. But why? Why does nature hold this particular prize just out of reach? The answer lies in one of the fundamental rules of physics, the third law of thermodynamics. It may not get the spotlight like the first or second laws, but it quietly governs the deep, chilly end of the temperature pool. In simple terms, the third law states that as a system approaches absolute zero, the entropy or disorder of that system approaches a constant minimum. But more importantly, it implies something very inconvenient. You can't reduce the temperature of a system to absolute zero through any finite number of steps or within a finite amount of time. In other words, no matter how clever your cooling techniques are, there will always be some stubborn residual motion you can't quite eliminate. It's like trying to turn off the last flickering light in a room where the switch keeps moving just out of reach. You can dim it, suppress it, quiet it down until it's barely glowing, but actually switching it off? Not going to happen. The problem is partly mathematical. As you cool something closer and closer to absolute zero, the energy you need to remove per degree gets smaller, but the effort required to remove it gets larger. The system becomes increasingly reluctant to give up that last bit of heat. Eventually the process becomes inefficient to the point of absurdity. It's a bit like trying to clean your room by moving the mess into smaller and smaller boxes forever. Sure, you're getting more organised, but the clutter never truly disappears. It just becomes more refined. In practice, this means that every time we try to shave off another fraction of a degree, we hit diminishing returns. Laser cooling, evaporative cooling, adiabatic demagnetization, they all get us closer, but each step forward requires exponentially more energy, more time and more precision than the last. And just when you think you're almost there, the finish line moves again. There's also a quantum mechanical reason absolute zero is unreachable. According to Heisenberg's uncertainty principle, you can never know both the position and momentum of a particle with perfect accuracy. If atoms were to come to a complete stop, you'd know both exactly where they are and exactly how fast they're moving, which would break the rules. Quantum mechanics doesn't allow that kind of certainty. So, even the most chilled out atom must retain a little jitter, a faint reminder that uncertainty never fully freezes. But what if we just build a better refrigerator? Well, cryogenic systems can only cool something by transferring its heat somewhere else. Typically, that means moving heat from a material to a refrigerant, like liquid helium, which then evaporates, carrying the heat away. But even this method has limits. Once the refrigerant and the material are nearly the same temperature, heat transfer slows dramatically. It's like trying to cool your soup by blowing on it with warm breath. Eventually, your efforts plateau. Evaporative cooling is another technique used in labs to cool gases to ultra-low temperatures. It works on the same principle as sweat. Let the warmest particles escape, and the rest cool down. But again, this works best in the early stages. The colder you get, the fewer high-energy particles remain, and the whole system becomes sluggish. And then there's adiabatic demagnetization. This process involves aligning the magnetic moments of particles using a strong magnetic field, which reduces their entropy. Then the magnetic field is reduced while the system is thermally isolated. This causes the system to cool, because the particles stay in a low entropy state. It's a brilliant method, but again, not perfect. Eventually the system hits a floor it can't push through. Think of it like trying to freeze a lake by standing over it with a single ice cube and a great deal of determination. You might make a dent in the temperature, but the laws of thermodynamics are unfortunately unimpressed by enthusiasm. Despite all this, scientists have come impressively close. Laboratories have chilled atoms to within a few billionths of a Kelvin above absolute zero. That's nanokelvins. At those temperatures, atomic motion slows to a crawl. Entire systems of atoms start to act like single unified entities. It's the birthplace of exotic states of matter like Bose-Einstein condensates, where particles merge into one quantum wave. Truly spectacular, but still not zero. Why does this matter, aside from being a fun intellectual puzzle? Because these extreme temperatures help us understand the foundations of reality. Near absolute zero, matter behaves in ways that are otherwise hidden. The thermal noise of everyday temperatures masks the delicate subtleties of quantum behaviour. But when the heat is gone, when motion slows and entropy drops, we get a clearer look at how particles interact, how forces behave, and what matter is capable of when it has nowhere left to hide. We also gain powerful tools. Superconductivity, quantum computing, and even advances in materials science all depend on ultra-cold environments. The closer we get to absolute zero, the more refined our instruments become. These temperatures reveal the whispers of the universe, the tiny shifts and fluctuations that tell stories hotter systems never can. But even with these insights, absolute zero itself remains a boundary. It's not a goal to be conquered, but a horizon to approach. Like the speed of light, it marks a fundamental limit built into the fabric of reality. It doesn't matter how many decimals we add to our cooling achievements, we'll never quite erase the last flicker of motion. And in a way, that's oddly comforting. The universe doesn't deal in absolutes. Even its coldest places carry a hint of restlessness, a reminder that motion, uncertainty, and imperfection are not just unavoidable, they're essential. So the next time you hear someone talking about temperatures near absolute zero, remember that they're flirting with the edge of the possible. They're pressing their ear to the wall between known and unknown, listening for the faintest vibrations. And while they may never hear perfect silence, what they do hear tells them more than noise ever could. In the end, chasing absolute zero is a bit like chasing a mirage. You never arrive, but the journey itself is where the magic happens. And somewhere along the way, while moving the metaphorical mess into ever smaller boxes, you start to understand not just how cold the universe can be, but how beautifully strange it becomes when everything slows down. Deep space is cold, not your average winter in Siberia cold, but a kind of relentless, unblinking -250 degrees Celsius kind of cold. It's not just the absence of warmth, it's the absence of anything to hold it. There's no air to carry heat, no wind to chill your cheeks, and no cosy blanket of atmosphere to trap warmth. Just an infinite silent emptiness. And floating through that emptiness, against all odds, are some of humanity's most delicate creations, spacecraft. Now, you might think that space being cold would make it easy to freeze things solid, like tossing your leftovers into a giant cosmic freezer. But space doesn't work quite like that. The vacuum of space doesn't conduct heat well because there's nothing to conduct it through. In fact, if you put an object out in space, it won't immediately freeze. Instead, it will slowly lose heat by radiating infrared energy away. No molecules to collide with, no breeze to carry the heat off, just a gentle leak of thermal energy into the void. This means that keeping a spacecraft warm isn't just a matter of wrapping it in a thick coat. It's a precise balancing act. Too much heat and sensitive instruments fry. Too little and electronics fail, lubricants freeze, and batteries refuse to cooperate. It's like trying to keep a cup of tea warm in the middle of a desert night, with no air, no fire, and the nearest electrical outlet about 20 million kilometers away. So how do we do it? The first trick is insulation. Spacecraft are often wrapped in shiny, crinkly-looking layers of material called multi-layer insulation, or MLI. If you've ever seen a satellite or an astronaut's suit, you've seen it. It looks like gold or silver foil depending on the coating. But it's not just for show. Each layer reflects thermal radiation, and the multiple layers trap heat like an ultralight high-tech sleeping bag. It doesn't keep all the warmth in, but it slows the loss dramatically. Next up, internal heating. Most spacecraft generate their own heat as a byproduct of running electronics. Computers, sensors, batteries, all of them produce small amounts of warmth during operation. Engineers carefully design the systems to retain and distribute this heat where it's needed most, often using heat pipes or radiators to shuffle it around. It's a bit like using a laptop to heat your blanket, with wires that know where your toes are coldest. But insulation and passive heating only get you so far. For missions that venture into the darker reaches of the solar system, beyond the sun's warm embrace, spacecraft need a more robust heat source. That's where radioisotope thermoelectric generators, or RTGs, come in. An RTG is essentially a nuclear battery. It uses the natural heat produced by the decay of radioactive materials, typically plutonium-238, to generate electricity. The heat flows through a thermocouple, which converts it into electrical power. There are no moving parts, no fuel tanks, and no need for sunlight. Just a steady trickle of warmth and voltage, lasting for decades. RTGs are incredibly reliable, which is why they've been used on some of NASA's most distant and daring missions. The Voyager probes, launched in 1977, are still powered by RTGs more than 45 years later. As they drift ever deeper into interstellar space, far beyond the orbit of Pluto, their solar panels would be useless. But their little nuclear hearts keep beating, keeping their instruments warm enough to function and sending back whispers from the edge of the Sun's domain. The Cassini spacecraft, which explored Saturn and its moons, also used an RTG to survive the cold. Saturn is nearly 1.5 billion kilometers from the Sun, where sunlight is only 1% as strong as it is on Earth. That's not enough to keep things running, or thawed. Without its onboard nuclear heater, Cassini would have frozen solid before it ever saw the ring sparkle. Then there's the James Webb Space Telescope, a marvel of engineering that lives in one of the coldest operational environments imaginable. Webb doesn't want to stay warm, it wants to stay cold. Very cold. Its instruments are designed to detect infrared light, which is essentially heat radiation. Any warmth from the telescope itself would create noise and obscure its view of faint cosmic signals. To stay chilly, Webb uses a combination of deep space exposure and a gigantic sun shield the size of a tennis court. This 5-layer shield blocks light and heat from the Sun, Earth and Moon, allowing the telescope to cool passively to around 40 Kelvin. That's minus 233 degrees Celsius. One of its instruments, the mid-infrared imager, is even actively cooled using a cryo cooler to bring it down to about 7 Kelvin. That's just a hair above the cosmic background temperature, a cosmic cold front custom built. Designing for these conditions is not something you do lightly. Engineers must account for materials contracting as they cool, lubricants freezing, and components becoming brittle. Traditional grease doesn't work well at minus 200 degrees. Instead, spacecraft use dry lubricants, things like molybdenum disulfide or graphite, or specialized materials that don't freeze at all. Cables must be flexible enough not to snap, and electronics must be shielded from extreme temperature swings. It's a little like building a toaster that works inside a freezer the size of the solar system, and then asking it to send you daily updates without ever malfunctioning. No pressure. The testing phase is equally intense. Before launch, spacecraft are placed in thermal vacuum chambers that simulate the environment of deep space. Engineers expose them to cycles of heating and freezing, mimicking what the vehicle will experience as it rotates or travels through shadowed regions. Every component is poked, prodded, shaken, and chilled, often for weeks on end, to ensure nothing breaks, cracks, or suddenly decides to stop working halfway to Jupiter. Yet even with all this careful preparation, surprises still happen. When the Hubble Space Telescope was first deployed, its electronics had issues regulating temperature, leading to some early hiccups in operation. Over time, engineers adapted, and Hubble went on to become one of the most successful observatories in history. Space is a harsh teacher, but a thorough one. And while the cold of deep space might seem like an obstacle, it also offers benefits. Without air, there's no corrosion, no weather, and very little degradation from the environment itself. Instruments can remain stable for decades. The very vacuum that chills also preserves. Voyager's golden records, quietly drifting through interstellar space, may last for millions of years, their grooves safe in the freezing stillness. In this way, cold becomes both enemy and ally. It threatens to break circuits and freeze joints, but it also allows for clarity, stability, and longevity. It demands respect, but it offers beauty in return. Images of galaxies in formation, infrared maps of star nurseries, and the distant pulses of dying worlds. Deep space travel, then, is not just about motion. It's about endurance. It's about building machines that can survive a world without warmth, a darkness so vast that even the heat of a small light bulb seems luxurious. And yet, with careful design and a touch of radioactive ingenuity, we've learned not just how to travel through the cold, but how to thrive in it. So when you think of spacecraft hurtling through the void, imagine not just their speed and distance, but their quiet warmth, an inner glow, barely visible, surrounded by a universe that never stops trying to turn out the lights. And still, they shine. There's something undeniably magical about the idea of cryosleep. It's the classic sci-fi solution to a very real problem. How do you send people on a journey that takes decades, maybe centuries, without them going completely stir-crazy, running out of food, or aging beyond recognition? The answer, in countless books and films, is elegantly simple. Just freeze them. Pop them into a futuristic pod, press a button, and they drift off into a perfectly preserved slumber while the ship cruises through the void. No bathroom breaks, no hunger pangs, no long philosophical conversations with the ship's AI. Then, decades later, they wake up refreshed, rested, and maybe even wrinkle-free, ready to explore a new planet or battle space aliens, whichever happens to come first. But back on Earth, things are a little more complicated. The notion of cryosleep, or more technically, suspended animation, isn't entirely fantasy. In biology, there are many examples of organisms slowing down their metabolism to near zero levels in response to extreme cold. Arctic frogs, for instance, can survive being frozen solid during winter, their hearts completely stopped, only to thaw out and hop away in the spring as if nothing happened. Certain turtles, insects, and fish pull off similar feats, essentially pausing their internal clocks until conditions improve. Nature, it seems, has figured out a few tricks. Humans, on the other hand, are not built for freezing. Our cells are full of water, and when that water freezes, it forms sharp ice crystals. These crystals puncture cell membranes like tiny daggers, causing catastrophic damage. The result isn't a gentle nap. It's more like turning a living thing into a shattered popsicle. To get around this, scientists have developed the process of cryopreservation, which involves cooling biological tissue to very low temperatures, typically minus 196 degrees Celsius, the boiling point of liquid nitrogen, while preventing ice formation. This is done using special chemicals called cryoprotectants. They act like antifreeze, replacing water inside cells and reducing the chance of damaging ice crystals forming during the freeze. Cryopreservation is already widely used in medicine. Sperm, eggs, embryos, and even small pieces of tissue are routinely frozen and stored for years without losing their viability. Some organs, like corneas and skin, can also be preserved this way for transplantation. But there's a catch. This process works best with small, simple structures. Whole organs, like hearts or livers, are much more difficult to freeze and thaw without injury, and whole human bodies are a much larger problem still. The main hurdle is that even with cryoprotectants, ensuring even cooling throughout a complex structure like a brain or a liver is extremely difficult. Parts of the tissue may cool too quickly, while others remain too warm, causing uneven freezing and cracking. Rewarming is even more hazardous. If done too slowly, ice can begin to form during the thaw. If done too quickly, thermal stress can cause tissues to fracture. Researchers are working on these issues. There have been advances in vitrification, a technique where cells are cooled so rapidly that the water turns into a glass-like state rather than crystallizing. In this form, damage is minimized and the structure remains intact. But getting that to work across an entire human body is a challenge of immense proportions. That hasn't stopped some people from signing up anyway. Companies like Alcor and the Cryonics Institute offer full body preservation, or just brain preservation, if you're feeling particularly minimalist. After legal death is declared, these companies begin the process of cooling and perfusing the body with cryoprotectants before lowering the temperature to liquid nitrogen levels. The hope is that future technology will be able to repair the damage and revive the person when science has caught up. It's important to note that this is not currently reversible. No human has ever been cryopreserved and brought back to life, not even close. It remains a speculative leap of faith, a kind of scientific time capsule filled with frozen hope. In contrast, the idea of short-term suspended animation is gaining traction in emergency medicine. Researchers have explored inducing deep hypothermia in trauma patients, cooling the body rapidly to below 20 degrees Celsius to slow metabolism and give surgeons more time to repair critical injuries. Some promising animal studies and very limited human trials suggest this may one day be a viable tool in emergency rooms, but it's more of a pause button than a full hibernation. We're talking minutes or hours, not decades. So what would it take to make cryosleep for space travel a reality? First, you'd need a way to cool a person to near zero metabolic function without forming ice crystals or damaging tissues. Then, you'd have to keep them stable for years, possibly generations, without power failures, system malfunctions, or unexpected thawing. Finally, and this is the tricky part, you'd need to rewarm them safely and fully restore their biological and cognitive functions as if nothing happened. Even if all the technical problems were solved, a host of ethical questions remain. If someone is frozen for 1,000 years and reawakened, are they still legally the same person? Who's responsible for their care? What if the world they wake up in doesn't want or remember them? And would it be right to send people off into deep space with only a vague promise that they'll wake up later? It's the philosophical equivalent of writing a check that your species hasn't yet learned how to cash. Then there's the psychological side. Even if the freezing and waking go perfectly, how does a human mind cope with skipping centuries? What happens to memory, to identity, to the sense of time? Are you still you if your last memory is from the year 2060 and you wake up in 3060? And yet, the allure remains. Cryosleep solves a very real problem. Long-distance space travel is impractical when measured in human lifespans. Without faster-than-light travel or magical wormholes, we're stuck with journeys that could take decades, even centuries. Suspended animation could, in theory, allow us to explore distant worlds, colonize other planets, or ride out long voyages without consuming endless supplies or going completely mad from boredom. There's also something deeply appealing about the metaphor. Cryosleep isn't just about freezing bodies, it's about preserving dreams, about tucking ourselves away for a future we hope will be kinder, more advanced, or at the very least awake and waiting. So, is cryosleep real? Not yet. But bits and pieces of the puzzle exist today in the form of cryopreserved embryos, vitrified tissues, and deep hypothermia experiments. The full picture, a safe, reversible, long-term stasis for human beings, is still science fiction. But like all good science fiction, it sits on the border of possibility, nudging at the edges of what might one day be real. Until then, cryosleep belongs to the realm of stories, filled with glowing pods, slow exhalations of mist, and the hope that waking up in a strange new world will feel a little like coming home. Our solar system, with all its fiery planets and swirling storms, has a quiet secret. It's also home to some of the coldest, most isolated worlds we've ever discovered. These frozen realms don't glow like the sun or sparkle with the colours of Saturn's rings. Instead, they lurk in the dark, icy, silent, and oddly mysterious. And yet, within their frozen crusts and slushy oceans, there might be something astonishing. Life. Let's begin with Europa, one of Jupiter's largest moons. At first glance, Europa looks like a cue ball dipped in cracks. Its surface is a smooth white shell of ice, etched with long reddish-brown lines that snake across its surface like veins on a marble sculpture. The temperature up there is not exactly tropical. Daytime highs hover around minus 160 degrees Celsius. The surface is solid ice, brittle and ancient, and exposed to relentless radiation from Jupiter's magnetosphere. But beneath that icy shell, something fascinating is hiding. Evidence suggests that Europa has a vast global ocean underneath its frozen surface. This isn't a puddle, it's a deep, possibly saltwater ocean, containing more liquid water than all of Earth's oceans combined, and it's kept in motion not by sunlight, but by the tidal forces of Jupiter's immense gravity. As Europa orbits its parent planet, it gets stretched and squeezed, generating internal heat. That warmth might be enough to keep the ocean from freezing solid, creating a potential habitat sealed beneath kilometers of ice. Then there's Enceladus, a small moon of Saturn that punches far above its weight in scientific intrigue. It's tiny, only about 500 kilometers across, roughly the width of the state of Arizona, but it's one of the most geologically active bodies in the solar system. Its surface is gleaming white, with fractures near the South Pole that vent enormous plumes of water vapor, ice particles, and organic molecules out into space. These geysers shoot hundreds of kilometers above the surface, forming a misty halo that feeds Saturn's E-ring. The temperature on Enceladus isn't exactly swimsuit weather either. The average surface temperature is around -200 degrees Celsius. But just like Europa, it's believed to have a subsurface ocean kept liquid by tidal flexing. And those plumes we've seen? They likely originate from that underground sea, meaning we've already sampled a little of what's hiding beneath. Cassini, the NASA spacecraft that orbited Saturn for over a decade, actually flew through the plumes and detected signs of organic chemistry, carbon-based molecules that form the foundation of life as we know it. Even farther out lies Pluto, the former 9th planet and current king of the Kuiper Belt. At a distance of nearly 6 billion kilometers from the Sun, Pluto receives less sunlight than a candle in a cave. Surface temperatures plunge to around -230 degrees Celsius, colder than anything else we've discussed so far. And yet, when the New Horizons spacecraft flew past Pluto in 2015, the little world surprised us. It wasn't just a frozen rock, it had mountains made of water ice, plains of nitrogen snow, glaciers, and even what looked like a giant heart-shaped region named Tombor Regio. The images showed a complex surface shaped by ongoing geologic activity, including possible cryovolcanism, eruptions of ice and slush rather than lava. Some scientists believe there could still be pockets of liquid beneath Pluto's crust, slowly freezing but perhaps not entirely solid just yet. The idea that these frozen moons and dwarf planets could harbour life beneath their surfaces might seem counterintuitive. After all, when we imagine life, we tend to think of warm, sunny environments, rainforests, coral reefs, and bubbling hot springs. But life on Earth has proven to be surprisingly adaptable. Microbes have been found thriving in the deep ocean, miles below the surface, where sunlight never reaches and pressure is crushing. Other extremophils live in the ice of Antarctica, in acidic lakes, and inside nuclear reactors. Life, it seems, is more flexible than we once believed. On Europa and Enceladus, the combination of liquid water, heat, and organic molecules creates a tantalizing possibility. If hydrothermal vents exist on their ocean floors, like the ones found on Earth's seafloor, they could provide energy and nutrients, supporting entire ecosystems. On Earth, hydrothermal vents host vibrant communities of tube worms, crabs, and bacteria, all sustained by chemosynthesis, life powered not by sunlight but by chemical reactions with minerals. Could something similar exist on another world? We don't know, not yet. But missions are in the works. NASA's Europa Clipper, set to launch in the 2020s, will orbit Jupiter and perform dozens of close flybys of Europa. It will carry instruments to map the surface, analyse the ice, and look for signs of habitability. Meanwhile, proposals for future missions to Enceladus are on the drawing board, perhaps even ones that could land and scoop up material from the geysers themselves. Pluto, being so far away and with such thin atmospheres and lower energy levels, might be less likely to support life. But it still teaches us something important, that cold worlds can be dynamic. They can change, evolve, and surprise us. They are not frozen tombstones drifting through space, but complex systems full of mystery and motion. The lesson here is simple but profound. Cold doesn't mean dead. The absence of surface warmth doesn't automatically rule out the presence of life. In fact, some of the best candidates for extraterrestrial life in our solar system are not the scorched rocks near the Sun or the red deserts of Mars, but these distant, icy spheres, sheltered, secretive, and quietly alive beneath their frosty skins. What's more, these environments might be more common than Earth-like ones. Icy moons and dwarf planets are found throughout our solar system, and probably beyond it too. If the ingredients for life can gather in their oceans, water, energy, and chemistry, then life could be more widespread in the universe than we dared to hope. Not on Earth clones orbiting sun-like stars, but in dark oceans beneath frozen shells, whispering stories we've only just begun to hear. It's a humbling reminder that our view of life and where it can exist is shaped by our own planet's quirks. Earth is warm and wet and sun-drenched, but that may not be the norm. The real heartbeat of the cosmos could be echoing from places we once dismissed as too cold, too quiet, too far. So the next time you look at an icy moon or a frosty dwarf planet in a photograph from some distant probe, try to see it not just as a lump of frozen rock, but as a hidden world, one that might hold not just secrets, but something breathing, moving, even evolving in the darkest, coldest corners of the solar system. If you've been drifting along in this chilly tour of the universe, you may have come across the term cold dark matter. It sounds appropriately mysterious and dramatic, like something whispered by astronomers over mugs of black coffee at 2 a.m, and it shows up all over cosmology textbooks, scientific papers, and even science fiction. But while the name suggests a shadowy substance locked in a state of deep freeze, the reality is both more abstract and more fascinating. Let's start with the dark part. Dark matter isn't dark in the way a shadow is dark or a cave is dark. It's dark because it doesn't emit, absorb, or reflect light. In fact, it doesn't interact with electromagnetic radiation at all. It's invisible, transparent, a complete ghost to our telescopes, but we know it's there because we can see what it does, even if we can't see what it is. Galaxies rotate in a way that suggests there's far more mass present than we can account for, with stars, gas, dust, and planets. Stars at the outer edges of galaxies move faster than they should if all the mass were concentrated near the centre. Something is adding extra gravity, something invisible. That something is what we call dark matter. It's the scaffolding that holds galaxies together and shapes the large-scale structure of the universe. So where does the cold come in? In cosmology, cold doesn't refer to temperature in the traditional sense. It doesn't mean these mysterious particles are frosty, or that they'd give you a chill if you could somehow shake their hand. Instead, cold refers to their speed, specifically how fast these particles were moving in the early universe. Cold dark matter particles are theorized to be non-relativistic when structure formation began, meaning they moved relatively slowly compared to the speed of light. This slow motion allowed them to clump together more easily, forming dense knots of gravitational glue that helped galaxies and galaxy clusters form. These clumps acted like seeds, drawing in normal matter, gas, dust, stars, and giving rise to the cosmic structures we see today. This is in contrast to hot dark matter, which would have been moving close to the speed of light in the early universe. Particles moving that fast would have smoothed over small fluctuations in density, making it difficult for galaxies and clusters to form. In theory, a universe dominated by hot dark matter would look very different, far more homogeneous, with fewer clumps of matter and less structure. Then there's warm dark matter, a kind of theoretical middle ground, not too fast, not too slow, like a bowl of cosmological porridge that's just right. Warm dark matter could still allow structure to form, but perhaps not quite in the same way or at the same scales as cold dark matter. Some cosmologists have proposed it as a potential solution to certain discrepancies between simulations and observations, such as the number of small satellite galaxies we see around the Milky Way. Now, the current leading theory, the one that best fits the data from cosmic microwave background measurements, galaxy surveys and gravitational lensing, is that dark matter is cold. But we haven't found the actual particles yet. They remain elusive. Many candidates have been proposed over the years. One of the earliest and most popular was the WIMP, or weakly interacting massive particle. As the name suggests, WIMPs are massive and interact very weakly with normal matter. If they exist, trillions of them would be passing through you every second without you ever noticing. Another candidate is the axion, a hypothetical ultralight particle that could form a pervasive invisible field across the cosmos. Then there are sterile neutrinos, a kind of ghostly cousin to the regular neutrinos we already know. Each of these possibilities fits slightly different models of dark matter behaviour, some colder, some warmer. Despite decades of effort, we still haven't detected dark matter directly. Scientists have built underground detectors shielded from cosmic rays, hoping to catch a single interaction between a dark matter particle and a normal atom. So far, those detectors have been eerily quiet. Space telescopes and particle colliders like the Large Hadron Collider have also joined the search, hunting for indirect clues. Still, the mystery remains. What we do know is that dark matter makes up about 27% of the universe's total mass energy content. That's over 5 times more than the ordinary matter we're made of. Everything we've ever touched, tasted, built or burned, all the protons and neutrons and electrons in stars, trees, toast and trombones, make up less than 5% of the universe. The rest is dark matter, and an even stranger thing called dark energy, which means that almost everything in the universe is made of something we've never seen. And yet, this invisible stuff plays a vital role. Without dark matter, galaxies wouldn't hold together, galaxy clusters wouldn't form. The universe would be a much smoother, emptier place, perhaps a little more polite, but a lot less interesting. Computer simulations that model cosmic evolution with cold dark matter produce structures that closely resemble the universe we actually observe. Dense filaments of galaxies stretching across space, enormous voids in between, and intricate web-like patterns of matter on vast scales. It's as if the cosmos is knitting itself together with invisible thread, and cold dark matter is the needle. That said, the cold in cold dark matter still trips people up. It's easy to imagine shadowy, frozen particles drifting through the universe in frosty clouds. But what it really refers to is dynamics, not temperature. If someone ever rebrands it, slow dark matter might be more accurate, though arguably less poetic. There's also the small matter of proving it exists at all. Some alternative theories have proposed doing away with dark matter entirely, instead modifying gravity to explain galactic rotation curves. These modified gravity theories, like MOND, short for modified Newtonian dynamics, offer interesting perspectives, but struggle to explain large-scale structures and the cosmic microwave background as successfully as cold dark matter does. So, for now, cold dark matter remains the frontrunner. Not because it's easy to find or elegant to explain, but because it works, mathematically, observationally and cosmologically. It's the invisible scaffolding upon which the entire visible universe is built. The unseen architecture that lets stars orbit their galaxies and galaxies dance across the void. It's humbling, really. The universe we see, the beautiful, brilliant part with stars and planets and comets and cats, is just a faint glow riding on top of something vast and unknown. Cold dark matter isn't just about temperature or even mass. It's about the parts of reality we've yet to grasp. The silent majority of the cosmos, voting in gravity's great election, holding everything together from behind the scenes. So the next time you look up at the stars, consider the invisible hand shaping their patterns. It may be cold, it may be dark, but without it, The universe would have no structure at all. If the universe had a bedtime story, this would be it. Not with a bang, but with a slow, steady sigh. Not fire and brimstone, but darkness and cold. This isn't the dramatic, meteor-filled, cinematic ending people often imagine. No exploding stars lighting up the sky one final time. No dramatic countdowns or ancient prophecies fulfilled. Just a gentle fading into stillness. The end, when it comes, may arrive as nothing more than a whisper. This theoretical finale is called the heat death of the universe, and despite its name, it has very little to do with heat as we experience it. It's not an inferno, it's actually the ultimate cold. A cosmic quietude where everything that could happen already has, and all that remains is a slow, unfurling stillness. To understand how we get there, we have to start with thermodynamics, specifically the second law. This rule, which governs how energy moves and transforms, tells us that entropy, or disorder, always increases in a closed system. Left to its own devices, the universe tends to spread out its energy evenly, like sugar dissolving into tea. Over time, differences in energy even out. Hot things cool, organized things decay. Complexity gives way to simplicity. That's entropy's way. Right now, the universe still has lots of interesting things going on. Stars are burning, galaxies are colliding, black holes are munching on the occasional unlucky gas cloud. There's light, warmth, motion, and imbalance, just the way entropy likes to play. But this won't last forever. Fast forward a few trillion years. First, the stars go. Big stars burn out quickly. Smaller ones, like red dwarfs, can last for trillions of years, but even their fuel eventually runs out. When a star dies, it leaves behind a white dwarf, a neutron star, or a black hole. Over immense spans of time, even white dwarfs, those glowing embers of former stars, will cool and fade into black dwarfs, radiating no light or heat. The galaxies themselves will grow dim, with no new stars forming and old stars winking out. The night sky will slowly lose its sparkle. The cosmos will become a quieter, darker place. Black holes, once thought to be eternal, are not immune to this process. Thanks to a prediction by Stephen Hawking, we now believe black holes slowly lose mass through a process called Hawking radiation. They emit tiny amounts of energy over time, shrinking ever so slightly with each passing eon. This evaporation is extraordinarily slow, but given enough time, vastly more time than the age of the universe so far, even the largest black holes will fizzle out and vanish into the quantum mist. What's left? Not much. Some particles, some lonely photons, a smattering of neutrons and protons drifting through space. The universe, by then, will be unimaginably vast and mostly empty. The temperature will approach absolute zero, hovering infinitesimally above it. At that point, no new stars will ignite, no structures will form, and no work will be done. Every gradient, every imbalance that once drove activity will be gone. This is heat death. Not a sudden collapse or catastrophic event, but a state of maximum entropy. Everything evenly distributed, no usable energy left to fuel change. The universe, still expanding, now contains nothing but a sparse soup of cold particles and faded radiation. It's a strange name, really. Heat death sounds like it should be fiery and final, but it's more like the dimming of a candle that was never relit. In thermodynamic terms, it's the point at which the universe reaches thermodynamic equilibrium, where every region has the same energy and no heat can flow from one place to another. Without those differences, nothing interesting can happen. No chemistry, no physics, no life, just silence. Of course, this scenario plays out on a timeline that is almost beyond comprehension. The death of stars takes trillions of years. The evaporation of black holes takes even longer, something like 1 Google years for the largest ones. That's a 1 followed by 100 zeros, a number so vast it barely fits inside a human imagination. If the universe were a person, it would have more than enough time to take a nap, wake up, read every book ever written, solve every crossword puzzle, and still have time left over to stare out the window for a few 100 billion years. It's also worth noting that heat death is just one possible ending. Some theories propose a big crunch, where gravity reverses the expansion and the universe collapses back in on itself. Others imagine a big rip, where the universe's expansion accelerates so much that galaxies, stars, planets, and even atoms are torn apart. But the heat death scenario is currently the most widely accepted, based on our best observations and the mathematics of entropy. Despite its melancholy tone, there's something oddly peaceful about it. No drama, no calamity, just the universe, completing its long journey from high energy and low entropy to low energy and high entropy. A gentle arc from creation to calm. And while the idea might sound bleak, an endless dark with nothing left to do, it also carries a kind of elegance. It's the universe following its own rules all the way to the end. The same principles that make stars shine and ice cubes melt also guide the cosmos into its final act. There's beauty in that consistency, a poetic sort of inevitability. Some physicists speculate that even this isn't truly the end, that in the deepest voids, quantum fluctuations might spark new universes, tiny bubbles of energy popping into existence, each with its own laws of physics, its own Big Bang, its own future. Perhaps our universe is just one in an endless series, a note in a melody that never stops playing. But that's speculation. For now, what we can say is that the universe seems to be headed toward quiet, toward stillness, not with a dramatic curtain call, but with a slow, cold fade into memory. And in that final stillness, in the cosmic hush that follows eons of light and motion, the story ends, not with a fiery apocalypse, but with a frozen whisper, a sigh of entropy echoing softly across an empty stage, the last breath of a universe that once burned with stars. If there's one thing scientists love, it's pushing limits. Whether it's smashing particles together at nearly the speed of light or staring at galaxies billions of light years away, there's a special kind of joy in chasing the extremes. But perhaps no pursuit is more quietly heroic, or more bizarre, than the effort to create the coldest temperatures in the universe. Not by stepping into deep space or visiting the Boomerang Nebula, but by dialing down the heat inside carefully engineered laboratories right here on Earth. This is not your standard freezer operation. We're not talking about a walk-in fridge for storing ice cream or the cold snap of a Siberian winter. These experiments involve bringing matter to within a fraction of a billionth of a degree above absolute zero. That's 0 Kelvin, or minus 273.15 degrees Celsius, a temperature so low it's hard to even imagine what cold means anymore. It's not just about still air or frozen toes, it's about atoms that barely twitch, it's about approaching the edge of motion itself. At the Massachusetts Institute of Technology, researchers have achieved temperatures as low as 500 picokelvin. That's 500 trillionths of a degree above absolute zero. In a 2010 experiment, they used a combination of laser cooling and magnetic fields to chill a gas of sodium-potassium molecules to these absurdly low temperatures. The result wasn't just cold, it was an entirely new realm of physics. At those temperatures, quantum effects dominate, and atoms begin to behave not as individuals but as collective waves. To reach this level of chill, scientists begin by cooling atoms with laser beams that are carefully tuned to the motion of the atoms themselves. The atoms absorb photons from the lasers, each one giving a tiny nudge in the opposite direction of motion, like a gentle hand slowing a rolling marble. Once the atoms are slowed down enough, they're trapped in magnetic or optical fields and further cooled using evaporative techniques, essentially letting the hottest atoms escape so the average energy drops. But laser cooling is just the opening act. To go even further, scientists must stack techniques like a delicate house of cards. Each layer, optical molasses, magnetic traps, forced evaporation, brings them a tiny step closer to that impossible goal. absolute zero. One of the strangest and most fascinating outcomes of these experiments is the creation of a Bose-Einstein condensate. First predicted by Albert Einstein and Satyendranath Bose in the early 20th century, this state of matter wasn't observed until 1995. When a group of atoms is cooled to just above absolute zero, they begin to overlap in their quantum states, behaving like a single, unified wave. It's as if they lose their individual identities and form one superatom. In this state, matter stops acting like particles and starts acting like something entirely new, almost liquid, almost light, and yet neither. The National Institute of Standards and Technology and the University of Colorado Boulder have been major players in this field as well. Their researchers have used ultra-cold atoms to explore fundamental questions about time, gravity, and the limits of quantum mechanics. Using atom interferometers, devices that measure the interference patterns of matter waves, they've studied how ultra-cold atoms respond to minute changes in gravitational fields or electromagnetic forces. And then there's NASA's Cold Atom Laboratory, which takes the pursuit of cold to an entirely new environment, space. In 2018, NASA launched this facility to the International Space Station with the goal of studying ultra-cold atoms in microgravity. On Earth, gravity eventually pulls atoms down, limiting how long they can be studied in free fall. But in space, those limitations vanish. Scientists can observe the behavior of Bose-Einstein condensates for much longer periods, watching how they evolve, drift, and interfere without the tug of Earth's pull. By eliminating gravitational constraints, the Cold Atom Laboratory opens up new avenues for studying fundamental physics. One area of interest is testing the equivalence principle, the idea that all objects fall the same way in a gravitational field, regardless of their mass or composition. Using ultra-cold atoms, researchers can perform exquisitely sensitive measurements of how gravity interacts with quantum matter, potentially revealing cracks in our current understanding of general relativity. At CERN, the European Organisation for Nuclear Research, most of the fame goes to high-energy experiments like those performed in the Large Hadron Collider. But CERN also dabbles in the cold. In particular, the antiproton decelerator uses magnetic fields and cryogenic cooling to slow down and trap antimatter, specifically antihydrogen. Studying how antimatter behaves compared to regular matter could shed light on why the universe is dominated by matter at all, despite theories suggesting the Big Bang should have produced both in equal amounts. Trapping antimatter requires extremely low temperatures, not just to slow the particles but to prevent them from touching matter and annihilating. These experiments are delicate, precise, and filled with drama, like keeping a tiny invisible snowflake intact in the middle of a bonfire. All of these efforts, whether in earthbound labs or aboard orbiting stations, point toward one goal: understanding how nature works when all the usual noise is stripped away. Heat, after all, is just motion. It's energy buzzing around, particles colliding, atoms bouncing. When you remove that motion, you remove the distraction. What remains is a universe reduced to its most fundamental behaviors. What do we learn in that silence? We learn how particles communicate, how time can stretch and bend in quantum systems, how superconductors carry current with zero resistance, how information might be stored and transferred in quantum computers. We begin to glimpse the rules behind the rules, the soft hum beneath the clatter of the everyday world. The coldest experiments ever performed are not just scientific stunts, they are windows into the structure of reality. They reveal the invisible framework that supports all matter, all energy, all interaction. At room temperature, the universe is noisy, energetic, and chaotic. But near absolute zero, it becomes contemplative, revealing patterns that are otherwise drowned out by thermal chatter. And there's a kind of poetry in that. In the silence of near zero, atoms form unison, like a choir whispering in perfect harmony. Forces that seem disconnected become synchronized. Structures that look chaotic resolve into clarity. It's as if the universe, when cooled to its quietest state, begins to speak in a language we can finally understand. We may never reach absolute zero, but every step closer brings us deeper into the heart of physics. Every record-breaking chill opens up new questions, new technologies, and new ways of seeing. These are experiments in stillness, in symmetry, in stripping the world down to its simplest truths. They remind us that sometimes, in science as in life, the most profound revelations come not from fire and fury, but from cold and calm. Imagine a universe where warmth is a memory, where stars no longer shine, where no fire burns and no molecule stirs with the lazy twitch of thermal motion. It is not a place of chaos or catastrophe. It's not filled with crashing planets or supernovas clawing at the sky. No, this universe is calm, utterly, infinitely calm. It is the quiet after all songs have ended, a place where temperature, that great driver of motion and life, has settled as close to zero as physics allows, a fully cold universe. What would it feel like, this place? Not in the human sense of feeling, of course. There are no nerves to tingle, no skin to goosebump, but in the abstract sense, in the grand poetic shape of things, it would feel still, motionless but not dead, silent but not empty. The galaxies have stopped spinning, the last stars have burned out, the black holes have evaporated into a dusting of radiation so faint it barely registers. What remains are particles drifting in vast, ever-expanding space, with nowhere to go and no energy left to change anything. This is not a frozen hell. It is more like a cosmic whisper, a gentle end, like exhaling after holding your breath for billions of years. In a fully cold universe, entropy has won. Energy has spread itself as evenly as possible, and nothing is left to power change. Stars no longer fuse atoms. Planets, if they still exist at all, are dark and lifeless. Molecules no longer bump and bounce with heat. The background temperature of the universe has cooled to nearly absolute zero, minus 273.15 degrees Celsius. Only the faintest trace of heat remains, the echo of what once was. Could life adapt to this? Could something survive here, in this pure stillness? Life, at least as we understand it, is powered by contrast. Warm versus cold, high energy versus low, chemical reactions that drive metabolism and movement. Every living thing on Earth thrives in imbalance. Plants feed on photons from a hot star. Animals feed on plants or on each other, shuffling energy around like a cosmic relay race. Life is a tightrope walk of energy exchange. In a universe where temperature gradients no longer exist, where everything is the same everywhere, there is no flow, and with no flow there is no work. Without work, no metabolism, no thought, no life. Even if a life form could somehow insulate itself perfectly and store energy for trillions of years, it would eventually spend that energy. Then it would join the great stillness. Of course, speculative thinkers have imagined exotic forms of life that might arise in the far future, beings that flicker into consciousness once every quadrillion years, powered by fleeting bursts of quantum fluctuation, living lives as brief as soap bubbles. But these are musings of science fiction, dreams whispered at the edge of physics. In practice, life seems intimately tied to warmth, to energy, to the dance of particles in motion. And yet, the idea of a universe without warmth is not entirely bleak. There is a strange elegance in the image, a cosmos that has lived a full, fiery life and now rests in perfect equilibrium. It is not mourning, it is resting. All the battles have been fought, the stars have told their stories, the galaxies have pirouetted across the void, and now, like dancers after a performance, the universe lets the curtain fall. There's a kind of peace in that. No rush, no noise, just vast cold space, humming ever so gently with the memory of light. We often associate cold with discomfort, frostbitten fingers, long nights, silent streets, but taken to its cosmic extreme, cold becomes something else. It becomes a stage where the deepest truths of the universe can be seen clearly, where heat and light no longer cloud our view, a place where matter becomes minimal and what remains is pure geometry, pure structure, pure time. It is here that the poetry of physics becomes most profound. In this frozen quiet, we can ask questions without expecting answers. What is the shape of a universe that no longer changes? What does time mean when nothing moves? When there is no heat, no clocks ticking, no atoms vibrating? What becomes of duration? These are not just scientific questions, they're philosophical. They nudge at the limits of understanding, the edges of consciousness. When you think about the cold end of the universe, you're not just thinking about temperature, you're contemplating the nature of existence itself, what it means to be when the last flickers of doing have gone out. And still, even in that silence, there is beauty. The symmetry of space stretched across unimaginable distances, the quiet dignity of particles content to drift, the persistence of gravity, holding on until the very end. There is something deeply moving about a universe that doesn't rage against the dying of the light, but simply allows itself to cool and rest. It's a reminder that not all endings are violent. Some come slowly, like winter settling in, not with a roar, but with a hush. The cosmos doesn't rage. It drifts, frozen and eternal. And yet, even as we imagine this final chapter, we're still here, warm, awake, breathing in a sliver of time when stars still shine and molecules still hum with life. Our tiny planet is perched in a very special moment, a moment when warmth still flows and energy still dances. That in itself is worth appreciating. In the grand arc of cosmic time, our warm, glowing now is brief, precious, and extraordinary. Perhaps that's the most meaningful takeaway from imagining a cold universe. It reminds us how rare warmth really is, how fragile, how beautiful, how worth cherishing. Because one day, if the theories hold true, warmth will fade. And when it does, the universe will close its eyes, not in sorrow, but in peace. Until then, let the stars burn brightly, let galaxies twirl, let particles collide and people dream. The universe is still warm, for now, and that, in the face of all that cold waiting out there, is nothing short of miraculous. The coldest places in the universe are not cruel or chaotic. They do not snap or burn or roar. They simply are, silent, elegant, untouched by heat or haste. From the impossibly frigid breath of the Boomerang Nebula to the calm hush of intergalactic space, we've wandered together through regions where the laws of nature slow and soften, where heat forgets to rise and even time seems unsure of its pace. These are not places you can visit with a suitcase and a camera. You wouldn't survive long, not without an enormous heater and quite a bit of luck, but their beauty lies not in comfort, but in perspective, in how they stretch our understanding. They teach us that cold is more than absence. It's a different kind of presence, a way of existing that's still and contemplative, a frozen ballet of atoms moving less and meaning more. We've explored icy moons hiding secret oceans, spacecraft wrapped in thermal blankets against the dark, and laboratories here on Earth creating temperatures unimaginably close to absolute zero. We've seen helium crawl up the sides of beakers, electrons glide without resistance, and atoms move in perfect quantum harmony. We've even peered into the future, when stars will have blinked their last, and the cosmos itself will slip quietly into an endless nap, a universe without warmth. And yet, in all this stillness, there is wonder, the kind of quiet that invites reflection, not fear, a whisper rather than a warning. There is something deeply human about imagining the coldest edges of reality. It humbles us, certainly, but it also connects us to something timeless. We are creatures of warmth, drawn to light and energy. And perhaps that's why the idea of cold, true cold, touches something profound. Because in dreaming of the universe's frozen places, we find contrast. We remember how rare our warm little moment really is. Even now, as you rest, wherever you are in the world, whatever time it may be, I hope this journey through cosmic chill has brought you some comfort. Maybe it sparked a flicker of curiosity, or maybe it simply helped quiet the noise of the day. If your eyelids are heavy and your thoughts are floating, that's perfectly all right. You're drifting now, just as the stars drift, just as heat itself once did through the fabric of space. And before you slip fully into sleep, I'd love to ask again, where are you watching from tonight? What time is it there? What does the sky look like above your home? Whether you're nestled under blankets on a winter evening or catching a nap with soft sunlight warming the curtains, it's a beautiful thing to know we're all looking out at the same sky, the same universe, the same stars glowing faintly against the cold. If you've enjoyed this journey, if it brought you calm or helped you feel a little more connected to the cosmos, I would be so grateful if you gave this video a like and maybe even subscribe to The Sleepy Scientist. It's your kindness and curiosity that keep these quiet explorations going. As the stars breathe frost and the void falls still, may your thoughts drift gently into the frozen cosmos. Sleep well, dream deeply, and remember, the cold may be vast, but so too is the wonder it carries.